In our earlier discussions of the change in electric potential, we emphasized the connection to electric fields along some path from the initial point of the path to the final point of the path. Today we'll focus on the fact that different paths between the same initial and final points lead to the same result, the same change in electric potential. We'll illustrate this with a specific case. The case of the change in electric potential due to a point charge as the source of the E field. However, this general result, this path independence, holds for electric fields due to any configuration of source charges. Consider a charge capital Q greater than 0 located at a point in space. Let's consider two such observation locations labeled I and F with corresponding position vectors. These locations are the endpoints of some path in space. Specifically, I is the starting point, the initial point of the path, and F is the endpoint, the final point of the path. The change in electric potential delta V is minus the integral of the scalar product of the E field times dr. In other words, we're taking the scalar product of vector E at small displacements dr at various points along the path and summing up all those scalar products along the path by integrating. Now one might think that if a different path between the initial and final positions is chosen, we'd end up with a different result. After all, not only is the second path different from the first, the electric field along that second path could be quite different from the electric field along the first path. However, we know how to work out this integral for the case of the E field due to a point charge source, and here is the result, which depends only on the endpoints of the path. That means besides these two paths, there are an infinite number of different paths we could consider starting from point I and ending at point F. All would have the same delta V. As we just mentioned, this property of delta V, the path independence of the change in electric potential, given the same starting and endpoints of the paths, is very general and applies to electric fields from many different configurations of source charges, not just this particular case. Here's a very important consequence of this path independence. Consider the same point charge, but now with point I serving as both the starting point and end point of the path. That is, the path makes a round trip. What is the change in electric potential in this case? We can work this out explicitly for a point charge, and we see that delta V is 0. This is also a very general result. For any round trip path, delta V is 0. This is a statement that energy can't be created or destroyed. Energy is conserved. Let's do an example that uses these ideas. Consider the straight line path that starts at point A and ends at point B, passing through the metal sphere as shown here. What is the change in electric potential along this path? That is, what is V sub B minus V sub A? Notice here that points A and B are the same distance from the center of the sphere. Stop the video here and take a few moments to try to answer this question before you continue. Now we know from our earlier discussions that in equilibrium, the sphere's charges will be uniformly distributed on the sphere's surface. That means the E field inside the sphere is 0, and the E field outside the sphere will look like that due to a point charge with all the charge located at the center of the sphere. So along the straight line path from A to B, the electric field is changing. We could still figure out the electric fields and work out the result for the change in electric potential. However, let's use path independence of delta V to choose a different path that allows us to calculate delta V more easily. And let's consider specifically the semicircular path that goes from A to B as shown, and consider computing delta V like this. Now, on this path, the electric field looks like that due to a point charge. For the negatively charged sphere, E is radially inward and, importantly, always perpendicular to the vector dr on this path. So, vector E dot vector dr is 0 everywhere along this semicircular path, and therefore delta V from A to B is 0. Alternatively, we could work this out a different way. We could use our expression for the change in electric potential for a point charge, and since points A and B are the same distance from the center of the sphere, delta V must be 0. So the correct answer here is V sub B minus V sub A is equal to 0. That's it for this lecture. In our next lecture, we'll work out 2 examples involving the concept of electric potential.